I want to introduce myself and also my co-partner. Let me stand up. So I'm Bob Zuber. I'm from Raleigh, North Carolina. I'm one of the product managers for IBM, and we just launched, not just launched, we launched what we call our X5 product line. A little lower, a little lower, a little lower. Yeah, that's better, thanks. Back in March. It's a brand new portfolio, and I'm going to take you through that portfolio along also with some details in virtualization, and then my partner in crime will be, go ahead. Oh, you don't have a...
Oh, I'm not on.
You're not on. You're not live. Turn him mic on, too. Got him on also?
So I'm Claude Barrera, and I'll be going through storage after Bob gets done with the server piece.
Great. So we're going to go quickly. Let's pass that slide here. So we always talk about, PCs. We always talk about servers and stuff like that. And one of the things I want to make sure that people understand is that my daughter's always like, these servers are PCs, right? And I'm like, well, they were born out of the PC, but reality now is that servers are far beyond just the PC. And they actually have taken a couple turns in their evolution. They've gone from PCs. Anybody ever have the old XT or even the PC before that? Yeah, few of us actually in college days had actually punch cards before these things came into existence, right? So I remember those too, and even punch tapes. But this has evolved over time, and it's turned on its side a number of times. We've got to the point where now blades are, integrated, and there's some new thinking about in regards to disaggregating the components. When we talk about servers, when we talk about the system itself, and it was always built upon a couple different components, namely the processor, the chipset around the processor, some I/O, memory, and storage. Those are basically container or the building blocks, and then likewise also the container itself, the mechanical device. But the new thinking now is that we need to start looking at changing and being more purpose-built, having systems that are much more about the utilization rates, or about the memory utilization, or even better yet, the memory bandwidth capabilities. So you're going to see a lot of systems coming out that are going to be very, not niche products, but they're very purpose-built for that specific type of workload, ranging from the processor, along with the chipset, along with the memory subsystem, and then likewise also the I/O subsystem that gets married to all that. So you're going to see a lot of new technologies coming out, like solid-state drives. You're going to see a lot of emphasis in that regards. It's all about getting better utilization rates and marrying the hardware to the actual workload to ensure that you're getting the most optimal and best performance of that. A lot of people are always worried about, years past, it was always about the performance of the system. And when we talk about performance, it's always how fast it goes. Now everyone's really oriented towards miles per gallon. How fast can it run, but most economically, more efficiently. And then likewise, you actually see some people are saying, hey, can the system actually become like two cars and be a fast Maserati or Ferrari, but then turn its character and change at nighttime to be more about a Prius. Anybody drive Priuses here? Oh, good. I can a whole bunch of Prius jokes about Priuses now. All right, so let's go back. Animations never work, but it's okay. Half the slide's missing, but that's okay. IBM has a very large portfolio ranging from our enterprise class servers, our blade centers, our rack and stack machines, and then lastly our iDataplex. We're going to talk about the enterprise class today because that's the most recently announced product. We also have a couple other products that are coming out like iDataplex and whatnot, but the large emphasis here is all about talking about how we're changing the building blocks and making these things a lot faster, not only in the processing speed, but more importantly, marrying it to the other resources that are inside that system. And when we look at that, the workloads that we're talking about are the ones that are demanding larger and larger systems. They're coming off of antiquated systems, maybe the older, Spark systems and whatnot. And when you look at the workload itself, it drives certain type of characteristics, not just about the processing speed, but more importantly, how much an SLA, or maybe even more importantly, how much more reliable is one platform versus another platform, or better yet, how much memory can one platform have versus another platform. And we talk about the capacity levels. We'll show you the systems themselves. They've gone dramatically from 256 gigabytes of memory now to a terabyte of memory. It's huge. So this performance is all around marrying the best components to those workloads and getting the most optimal mix of that environment. And then likewise also, it really, when people talk about having high availability capabilities in the software also has to be married to the hardware. Being able to have very highly resilient machines married to the very resilient software is a great match for a lot of people. When we talk about resiliency, it's all about marrying the two, because having one versus another, in the past years ago, we used to have very resilient systems, but the operating systems would always go down, and that didn't bode very well from an IT perspective. And likewise, having software running on machines that go down from a hardware point of view, and having non-redundant power supplies, etc. It's great to have software that's really resilient, but if the hardware is continually going down, you have to have a perfect marriage. So what IBM has done is actually introduced back in March and May time period, we've actually brought out 3 new products. In the past, our enterprise class systems were always our 4-socket, what we called our 3850. Our enterprise system was always a 4-socket, Intel-based. It was very, very high-end. Actually, you could scale from 4-socket all the way up to 16 and actually even to 32. And we said, we're going to take that and bring it across the portfolio. So what we did was we introduced not only a 4-socket, we also said we're going to take that same concept of the 4-socket building block and apply it to blades and also to a lower-end rack solution. I mean by lower end, but a smaller form factor. And we had a lot of customers who were asking us to do machines having enterprise class capabilities, but at a lower price point and also a lower form factor. And that's where the 3690 comes into play. With that also, we introduced 3 new innovations. We actually have a memory drawer that can expand and add additional memory beyond the system capabilities, beyond the actual base system. It actually can scale that, and actually have 32 in the rack and 24 in the blade. And it comes in 2 flavors, both rack and blade. And then we also have our X-Flash. So as we look at having more and more cores and more processing power inside the system, you have to marry that with the other resources, namely memory and I/O. And the I/O, the flash capability, or X-Flash, is actually taking solid-state drives and incorporating that and getting even faster I/O perspectives. And then lastly is our Flex Node, being able to make it flexible and make it look like one system at maybe in the afternoon versus another system during the day, or even at night. So around that is all about the Intel processor. The X5, X4, all the generations we've had, and actually we've been doing this for 10, 12 years. My daughter was probably in grade school when I first came out with this. I've been doing this for quite a long time, and now she's in college, and everybody asks me how my wife's doing in transitioning from college. I'm like, not as well as my transitioning in my products, but nevertheless, we've been doing this for quite some time. Intel has a broad breadth of Intel processors from a portfolio perspective. There is what we call the 5600 or the 2-socket Westmere class systems, and then there's also the 7500 class or the Nehalem EX class. There's also a new processor that's actually the same as the 7500, but only in a 2-socket variety. And there's going to be some confusion in the marketplace when you look at 2-socket EP versus 2-socket EX. The big delta differences are really the number of cores, and then likewise also the cache levels, and lastly the QPI links and the capabilities like memory controllers and that kind of stuff like that. The 6500 is intended to be a 2-socket variety, can grow into a 7500 class from a system point of view, but more importantly, the difference between these 2 classes of processors is really about the fact that this is more commodity-based and this is more enterprise-based, and we'll talk about what that really means from a system point of view. When the 7500, what it really gravitates towards is larger enterprise class workloads, namely also from a virtualization point of view, virtualizing even more workloads than it has in the past. Its capabilities range from 8 cores all the way up to 16 cores from a hyper-threading point of view. You have up to 256 from a socket perspective. You have 256 gigabytes per socket. And then more importantly, you have twice the number of I/O capacities, and then more importantly, the RAS capabilities in the 7500 class that you don't have in the other class systems. Marrying that to the VT technologies is a perfect platform for both large-scale mission-critical virtualization platforms, databases, ERP, all those big workloads, mission-critical kind of things. What that really means from a dollar perspective is as you load up more and more of these, let's say, VMs, you get a better cost per VM ratio, and ultimately gets the best consolidation ratio. But that is against everyone's trustworthiness of, hey, how many VMs can I put on one platform? And we'll talk a lot about that. The headroom for peak and unpredictable workloads, this is one of the biggest considerations. I've done talking to a lot of customers all about peak performance, and it typically was always oriented towards the processor. How many cycles do I have? How many VMs can I host? And through time, what has happened, you'll see that through virtualization 1.0 to 2.0 to 3.0, people are looking at not the most number of VMs, but more importantly, the most efficient VMs. And that really revolves around the fact that as they see their workloads peak, it's not just the CPUs that are peaking, it's also the memory peaking along with the I/O. So having a perfect mix between the two is very, very important. We'll talk a little bit about headroom, and then more importantly about peak and average utilization rates. And that's really the most important thing in regards to, from a capacity point of view, from virtualization. And then lastly, live migration, the ability to take VMs and live migrate them across the entire Intel portfolio, starting with the 5500 class. It gives the customer the ability to take those workloads and migrate them across both platforms very easily. So they can take it from the EP class all the way up to EX and then likewise back again. So it's very optimized from a virtualization point of view. Now, in our other IBM portfolio, we've always had these highly resilient type of processors. Intel has been putting a lot of resiliency into their processor, and they kind of fall into 4 different categories: memory, I/O, CPU, socket capabilities, and then quick path interconnect. What this really means is that as we start loading up and having more and more VMs on these platforms, it's really imperative that we make sure this is as resilient as possible. Being able to look through the CPU stack and determine when an error is going to occur, or more importantly, maybe even a faulty information. You say, hey, it's a suspect. It's not something that, it's maybe not an error, but it may not be correct. And so being able to have things like being able to do assisted in-memory migration or failed DIMM isolation, or even down to the address parity, this is all capabilities that are built into the Intel processor to give you more resiliency. Being able to do like rollbacks. Anybody ever do a database rollback ever? Databases have the capabilities to keep things in logs in the queue, and as you go down the CPU stack and you start doing things in the operation of the database, you can get to a point where the database fails. You can actually roll it back and start over again on some other node. That's the kind of capabilities that we're talking about. We want to be able to take these type of information, run it on a processor or on a core or even on a single thread of execution, and have it replayed someplace else without you guys even knowing about it. It's like having a car. I tell my VP, it's like having a car that's actually driving down the road and one of the cylinders goes. Now, many times we ride on the road and the cylinder blows and we have to pull off to the side. And I don't know about you guys, have you ever had a timing belt change in a car? My old Mustang just died on the road and I can't stand it. Well, guess what? This type of machine would actually shut the core off and migrate all that workload that was running on that core or on that socket and move it over to one of the other cores or other sockets that are running inside the machine. So it's like having a cylinder fail in your car and continue driving down the road. So instead of having an 8-cylinder, now you have a 7-cylinder, or if you're lucky to have a Ferrari having like a 12-cylinder, you get now 11. But more importantly, it's constantly running and still going. And you still get to your end result, but in a degraded mode. That's the kind of capabilities that we're talking about. And it revolves all around the memory subsystem, the I/O piece, CPUs, and the interconnect between those processors. If there's a failed component from a packet retry, you can actually take that packet and send it across another QPI link. All those new RAS capabilities are making this a much more resilient processor and being able to give you that trustness in regards to how many VMs I can put on this platform. So as we migrate across lots of different, let's say, realms of virtualization from 1.0 to 2.0 to 3.0, it's really all about, people who are doing virtualization 1.0, it's all about the operational expense of, taking a whole bunch of physical systems and making them into virtualized. We've all done that in this room. I mean, people have been doing virtualization for quite some time on VMware, so that's typically where a lot of these people are. But when you get to this area, it's more about the dynamic resource allocation, being able to understand as you vMotion something, where it's most appropriate to vMotion to. Not just simply move it to another system, but more importantly, move it to a system that may have the characteristics that you're looking for from that workload perspective. One that is much more efficient from a power consumption point of view, or all those details. The ultimate is the 3.0 space, the automation and reliability capabilities that we're looking at from a total automation point of view, being able to have a large cloud infrastructure and having every single type of system that's highly reliable or highly efficient, and be able to automate the workloads as they move about that environment, that cloud, and have it run appropriately on that platform. Being able to marry the workload that says, hey, I really don't care about performance, about the speed of execution, but I really care about the efficiency, how fast versus, how many miles per gallon. And that's in this space, and that automation is the next realm of what we're talking about. These platforms that we're doing right now today is all addressing this virtualization 2.0, and as we migrate up to 3.0, it's really important to understand the workload mix along with that platform. So from a system point of view, we've introduced, as I mentioned before, 3 systems, the 3850, HX5, and the 3690. You'll notice that there's also a very clear numbering scheme inside the name of that system to highlight, what is the X5 component. So all those systems always have an X5 in its name versus what the rest of our IBM portfolio has. The 4-socket 4U is a scalable 4-socket. It comes in 4U, and we'll talk a lot about that in regards to memory and whatnot. There's also the same exact thing we did in Blaze. We took this scalable concept, and we actually put 2 CPUs inside and be able to scale that to a 4-socket. And then last, we also have a 2-socket rack. This also goes from a 2U, it's exactly half of this 3850, called the 3690, to allow you to do the same things as 3850, but in half the space. The 3850, the big thing here was we doubled the number of drives. We went from 4 drives internally to now 8 drives. The memory DIMMs, we went from 4 trays of memory cards. It is exactly the same type of design now using DDR3 memory. We now doubled that, and that's the standard within the Intel processor. Each processor, from a Xeon point of view, can handle up to 16 DIMMs. Multiply that by 16, by 4, you get up to a terabyte of memory internally. Now, everyone always looks at the amount of memory inside these systems and go, terabyte of memory, that's a huge amount of memory to, from a virtualization farm point of view or even from a database point of view. Really, it's all about the memory bandwidth, though. It's not about the actual total capacity. If you talk to any DBA, we ask them, how many drives do you want? I want as many drives as possible. It goes as wide as possible. How big do you want them? 20 gigabyte, 30 gigabyte. Well, wait a minute, that doesn't really, we can't build those drives anymore. They're 200 gigabyte drives and 300 gigabyte drives. The emphasis really was, from a database point of view, was to go very, very wide because the IOs were very slow. They want to have lots and lots of lanes of opportunity to get to that data. The same thing is happening in memory. So when we talk about the memory DIMMs themselves, it's all about having not larger DIMMs, but more importantly, more DIMMs. Being able to have faster DIMMs that run consistently the same speed at 1066 across all of them, all 64, and also to the other additional memory DIMMs we'll talk about, the 32 more in that 1U form factor in the Max 5, being able to give you consistent memory speeds across all the DIMMs and giving you very, very wide distribution of those DIMMs. That gives you great opportunities to do things like when you do a vMotion, being able to move those VMs off of the core, throw it out in the pipe, get it out of the memory, and then throw it down the pipe and go to the next system. That bottleneck typically was in the past, was all about the memory. It wasn't things coming off the core. It was because the processors were always getting faster and faster. It was all about the memory speed and how much memory there was. Those big DIMMs, guess what? There's always one path to that DIMM. That slowed things down. And that was one of the things that we looked at and said, we really want to have systems that are enterprise class have to have more memory bandwidth. Lastly, we also have the I/O slots in the back, and we also have our power supplies. And power supplies are 2 1975-watt power supplies. And these power supplies, what's really important in the power supplies is not the, how many watts it is and whatnot, but more importantly, the efficiency levels. Back to that Prius. Those Priuses are typically, have anybody drive behind a Prius getting on the highway? You ever done that? I can't stand it because it's like this really slow on-ramp. So the curve of efficiency in old power supplies are very, very even curve of distribution. And when you look at that over efficiency, you say, hey, the efficiency versus the utilization of the system. Typical systems today are how utilized? 10, 12, if they're not virtualized. If they're virtualized, they're what? 45%? 60%? What are you guys running it at? 90%? You guys are never running at 90%, right? Well, if you look at that curve, the very low end of the thing, what was the efficiency of that power supply? About equal, about 12, 15% efficiency. So as soon as you plug that 1975-watt power supply in, you consume all that power, and you get how much out of it? About 200 watts. Okay, so now you get to the point where very inefficient power supplies. These new power supplies, though, are dragsters. They come out right off the line, very, very high, come very, very fast off the line, and they flatline, basically from the utilization of the system from about 15% all the way out to 98%. Very, very high level at 92 to 95% efficiencies. So having a fast car, this is really about the dragster of power supplies. These power supplies, the efficiency is really married to the workload now. And that's all about, when we looked at those components, it's all about getting the most efficient level of power supplies, memory DIMMs, all the components within that system. All right. We also took that and applied that to blades. We took a 2-socket blade form factor and actually married the two together. We have 16 DIMMs. We have our solid-state drives for booting purposes. We have 2 physical power two CPUs, the Xeon 7500 and 6500 class. And then we have our I/O slots in the back. We have 4 expansion slots giving you 2 of each, both CIOV and CFF implementations. The upper blade and the bottom blade are identical to one another. You can actually plug them together. As you can see here, there's a connector here that connects them together, so you take a 2-socket and make it look like a 4-socket. All right. You can also take that and marry it to a memory blade. So you take this memory blade, where we only had 16 DIMMs plus 16 having a 4-socket with 32, I can now also take that and plug it to a memory card or memory blade and now get another additional 24 plus the 16 to get to 40 for a 2-socket or 80 for a 4-socket. I can be very flexible in regards to how I marry these things together to give you the capabilities you need. More importantly, once again, building the system to marry to the actual workload. And we did exactly the same thing on our 2-socket. We took a 2-socket design, and we actually took a number of drives. We actually have 16 drives up front here. We have 2 mezzanines, upper and lower mezzanine. The CPUs are on the bottom mezzanine, and the upper ones are on top. Are just memory DIMMs. And that gives you 32 DIMMs on a 2-socket. It's a little bit different than a 2-socket 18 DIMM variety. We'll talk about the differences there. This also allows you to have flexibility in regards to the I/O. So that XFlash component. You actually can take 4 of these drives out. Instead of being SAS drives, I can actually pull those out and use solid-state drives. Since they're about 1.8-inch drives, they're very small. They look like little adapters, like PCMA adapters. They fit into the same spot of where 4 are. You get 8 of those solid-states. They come in 200 gigabyte drives. Now, remember that bandwidth story about the fact that as you go wide in regards to bandwidth, number of drives? DBAs today, when they actually look at having lots and lots of IOPS, they have to have thousands and thousands of drives. Well, that changes in solid-state technology. Solid-state is much faster. Well, today's drives are around 300 IOPS from a SAS drive perspective. These are 3,000 IOPS per drive. And as you multiply them up, you get bigger and bigger. The IOPS, number of IOPS that you have in here is tremendous. It actually goes up to 30,000 IOPS for some instances, where you actually have the adapter. So you can have in one system 500,000 IOPS. Well, that's a lot of IOPS from a database point of view. From a virtualization point of view, what does it do? Having fast processors, fast memory, and being able to have VMs come off the storage gives you greater possibilities in regards to being able to do more dynamic infrastructures, being able to have systems that come online faster and run extremely quickly. Now, on top of that, we've also added 2 systems, or added 2 Max 5s, both in a rack and a blade implementation, to give you that memory. Where I mentioned it before was in the blade. This is the rack implementation. It's the one you slice. We have it in the booth, and it's got 32 DIMMs, and it actually connects and has its own memory controller on board. It actually runs all these DIMMs at the same speed as the internal DIMMs, so all running at 1066. With that, we have one portfolio of products. We have a single HX5 blade, a 3690 rack, and a 3850 rack. Being able to connect these things gives you great flexibility. There's also these connectors out the system called QPI connectors, and those are taking the Intel QPI links that we have today that connect processors together. And we actually enhanced it a little bit to give us the ability to take cables and connect these things together, so I can take a 4-socket and marry it to another 4-socket and make it into an 8-socket. Or actually connect it to a memory drawer and get an additional 32 DIMMs or 64 DIMMs here plus another 32. And I get you all this flexibility in both rack and blades. Being able to have you have just 3 systems to give you a full portfolio of mixes of different systems, depending upon what your needs are. Now, on top of that, we also have, from an X5 point of view, we also have other platforms, namely our Westmere EP platforms. And this is our 3650 M3 and our HS22V. These are those processors we talked about before, which was that Westmere EP platform, that 5600 platform. And these are very similar systems. You'll see a 2-socket, looks just like a 2-socket 2, like the 3690, but it utilizes EP class. And so this is a non-EX5 system. It doesn't do scaling. It doesn't do the same kind of capabilities. But more importantly, it uses the Intel processor and gives you the ability to have different things that you can do from a virtualization point of view. Likewise, we had exactly the same thing on a blade perspective. So we're doing common things in regards to amount of DIMMs on one platform versus another platform. And when you look at it, it's very similar in design points. We have our power supplies. We actually have our fans, all our hot swap fans, and likewise also the memory DIMMs on top and the processors here. And then we have our I/O slots in the back. And the same thing from a blade perspective. Here, though, we actually have, we have our processors, our memory DIMMs, and we use solid-state drives up front to give the booting capabilities, but it's a very similar design. Doesn't scale, but it actually gives you a 2-socket 18-DIMM variety. Where you may want to use that, though, is that from a blending or from a positioning point of view, you have both racks and blades. So we have the 3690 versus the 3650. This is your flagship 2-socket EP class, and then you have your high-end 2-socket EX class. And then lastly are also our 4-socket that can also scale to 8-socket. So a very, very scalable platform. And from a positioning point of view, you can have different varieties of number of VMs, databases, et cetera. So this is all about having, maybe a cost perspective versus a pure performance perspective. And the same thing for the blades. We have the same kind of thing on an HS22V versus HX5. Now, how does that benefit from a virtualization point of view? We started looking at all the different ISVs in the marketplace, and one of them was very interesting was SAP. And we looked at, over the years, from a deployment point of view, back in 2001, it was always typically on single systems. And as you roll these out and having got more and more complex SAP deployments, they found the customers are finding that as they rolled those SAP deployments out, they were doing things like test and dev and QA. And then all of a sudden the systems multiplied, not just from doing 4 systems here, but now multiply that across multiple, like production environments to QA environments. And you can see all those start to multiply dramatically. The trend today, though, in 2010 is actually to virtualize all those. Take all those machines and now start virtualizing them. Maybe not on one single system, but more on a couple different systems. And it's all about doing multiple systems from an SAP point of view. Maybe you may have a dev, a test, and a QA, but you'll host all these systems on a single system. And so when we looked at it, we said, hey, there's different varieties, both the scale-up, both the EP class and EX class, and it's both a scale-out variety versus a scale-up variety. And they have different types of functions and features that you're looking for. Typically, in the EP class, it was all about having rapid deployment, slightly lower costs, not necessarily the most flexible, but more importantly, had a little bit of resiliency, had a little bit of flexibility in regards to the number of DIMMs, and got you fairly good performance. Then you go up to the other end and you say, hey, I might want to optimize and get more consolidations, get higher number of VMs, but more importantly, optimize that workload, and then take those legacy applications that were typically on the large single machines and move them into these type of class systems. And when you look at the performance of it overall, and that was the biggest question we had. We did a lot of studies and said, how was the performance overall from SAP? As you virtualize SAP on VMware, how did it perform? From a scalability point of view, you can see that you have the EX line versus the native line. So actually, the performance scaled very, very, very easily and very efficiently from when we start rolling out these new platforms. So from an SAP point of view, we're seeing a lot more customers deploy SAP virtualized than they are non-virtualized. It only makes sense. As you look at the larger systems, our larger Unix systems, they're always virtualized. Customers are accustomed to doing that. And they'll move that down into the Intel space. Where are they going to run that? They're going to run on Intel on what? On VMware. And now the big question was, how efficient would that be? And as you increase the number of cores, the number of CPUs, that scaling factor was it followed a very linear curve in that regards. So it's very, very, very realistic. So. And with that, I'm going to turn it over to Claude, and he's going to talk about the storage. Any questions so far? And we'll take questions afterwards also. So, here you go. What time we got?
We're good.
Okay, good.
Okay, so we're going to switch gears here a little bit and talk about storage, I hope. Where's the target? Oh, the target's over. Oh, that's the...
Pull it back to go forward.
Oh, okay. Ooh. Which way are we going here? There we go. Okay, so the main thing to talk about here with regard to storage in virtual machine environments is how one accomplishes all the promises or guarantees associated with enterprise storage. So in all the pictures we were just looking at, there were always embedded disks, embedded HDDs or SSDs inside the servers. And okay, that's easily done. And if you're living in a dev test environment or you have a limited amount of storage for that one particular server, you're running a web server or something like that, that may be all the storage that one particular application instance may need. and therefore embedded disk is fine, end of the storage discussion. But that's not how you build enterprise-class systems. Enterprise-class systems have to have continuity availability, they have to have data protection, they have to have disaster protection. If you're trying to build a 7 by 24 by 365 kind of system, almost all of the trick is around how you manage continuity to data. So put that over here on one side as sort of a statement of requirement. The other thing that's happening in the world is data is growing like crazy. So if you start looking at where are all the places where somebody might want to use a virtual server environment and map those against the kinds of applications that are growing big data, and along with big data comes the need for high availability because you've got lots of users, or because you're playing some important role in a business process or corporate governance or keeping the airplanes in the sky, something like that. You now have the enterprise storage problem. So as the world becomes more and more instrumented, we deploy more and more gadgets that collect information and act on it and assert control over the business world or the physical world. We accomplish that by bringing in lots and lots of data, computing on it, saving it, doing analytics on it. So the world is becoming a more and more data-intensive place. And as we look historically, the world began in the data center. You had limited numbers of people creating or accessing data. As we've stepped forward from distributed computing to the internet, to now where we talk about an Internet of Things, where the world is made up of lots and lots of sensors, already billions of sensors collecting data, in a number of cases, big complex objects, video, audio, medical images. So things that are not transactions anymore but are relatively large in terms of their capacity. We end up dealing with this issue of scale in the overall size of the data and the number of producers and the numbers of consumers. And if you then say, well, okay, if virtual servers are a good thing, if they're easy to manage, if they accomplish better utilization of my compute resource, then I want to map the enterprise storage requirements to a virtual server environment, and then you have to start addressing a number of these kinds of capabilities. So now talking about the specifics of enterprise data, not storage yet, but data, we've had this historical collection of ilities in the enterprise world for a very long time. So somebody back in 1970 would have put together the same list. We have to maintain availability of the data. We have to be able to move it around because one disk array might come off lease and another disk array has to start up. So I have to be able to move data from one machine to another, or to load balance, or to conduct distribution across multiple locations. I have to be able to protect from loss or corruption and apply security. And all of this has to be maintained at a particular cost point. So if that's the classical set of needs, when servers become virtual, we now have a new environment in which not only do we have very large scale, but we have unpredictability of demand in a particular storage device. So I've got this storage device and I've connected it to a whole bunch of servers, but as the virtual servers come and go attached to that storage device, the load being applied to the disk array is now highly unpredictable. And I may lose control of physicality. So if I no longer know which particular server is running which particular app at any particular instance, the question of where is my data physically, and therefore how do I assert protection in terms of security or disaster tolerance, the physicality of data location has now been broken. So if that's true about data, then what's true about storage? Well, what's true about storage is we've also had a set of classical requirements in the enterprise space for a long time, in particular static provisioning. So I wheel in a disk array, I cable it up to a particular set of servers, and those servers will apply I/O. I'm done provisioning. Well, in a world in which physical servers are attached to storage, but the virtual servers move around, the association of a particular virtual server to its data has to be maintained. So the storage layer now has to be a proper partner in the collection of applications that are created, laid on virtual servers, in turn on physical servers, and now allowed to address physical storage. So the kinds of capabilities that tend to show up as necessary, being able to apply workload balancing to storage, being able to dynamically respond to mixes of application workload across different interfaces, being able to take lots of snapshots turns out to be a very important thing because virtual servers tend to do that. They like creating new instances of themselves via cloning, and that turns out to be sort of a power use of things like snapshot function. Typically in virtualized environments, if you're doing hosting or providing something as a service, software as a service, infrastructure as a service, we now have the notion of multiple tenants within a storage environment, so multi-tenancy security tends to be important also. Okay, so with all of that as prelude, we now work our way into some real architectures. So this is sort of the first model that everybody sort of got started on as we started looking at how do virtual servers deal with enterprise storage environments. And the idea was that you've got a number of physical servers. They run hypervisors. The hypervisor sits up there. Underneath you have a SAN or a collection of NAS boxes. And there's a one-to-one mapping between the images of storage created by the storage layer to the actual virtual server. In a variety of different hypervisor environments, we call that either raw disk mode for VMware or image mode in some of the other environments. But by doing things simply like that, I've got a virtual server, it needs to see a disk, I create that disk out of the storage layer, things are good. Well, things are good until they start moving around. So in this richer picture over here on the right, we now introduce the question of, well, maybe storage virtualization, creating a virtual LUN or an image of an addressable piece of storage, is now to be done in the hypervisor layer itself. And once the hypervisor is in control of saying where the LUNs are and who owns them, it can be a party to a combination of server and storage mobility, which is one of the most important attributes of a good marriage between virtual storage and virtualized servers. One other thing to note, in this first column over here, we were talking about storage that's virtualized externally to the server stack. That turns out to still be a good idea over here. So it actually, in real practical implementations, and I'll show you a couple of pictures here in a second, the idea of stacked layers of storage virtualization turns out to be something that's useful because, first of all, your VMware environment might not be the only set of applications running in your enterprise. That's common in big enterprise environments. Another fact is that virtualization as performed in the hypervisor layer is relatively uninformed about the physicality of the underlying storage implementation. So if you need a virtualization layer to handle things like the physical removal of a box or the loss of a path and reconstruct of other assets or other paths to data, or the loss of a disk and reconstruct of a RAID array, and the performance rebalancing that has to be associated with that, that's probably not a function that's going to be implemented anytime real soon in the hypervisor layer. But this notion of combined server and storage mobility actually is something that plays up in that layer. So I've talked about a couple of the kinds of functionalities that come in play when you do the whole enterprise job. This is a more complete list, and it's not meant to be talked to in detail here. It's sort of meant to impress you with, how hard this stuff is. because if you fail in one of these things, if you don't do resource pooling well, you wake up one morning and you discover that all of your data, even the football scores, are on tier 1 disk and you're wasting your money. Or if you fail to do resource lifecycle management, you discover that all the old databases and all the old copies of stuff are sitting around on valuable storage and you're running out of that and you wish you had some free space. So there's a long list of things to be done. We, IBM, have some interesting products that map well to the kinds of requirements that we see in virtualized environments. So one is the SAN volume controller, which acts as a gateway between underlying disk arrays from just about any vendor up to the attached application servers. We also have a kind of an interesting box which has an internal grid architecture. It's built out of IBM x86 X-series servers together with locally attached disk for each one of those servers. The whole thing wrapped together as a storage cluster. So if you go down to our booth on the show floor, you can see one of these XIV machines and maybe play around with it a little bit. The thing that's really interesting about XIV from a virtual storage perspective is that it does load balancing extraordinarily well. It basically spreads virtual LUNs across all the arms in the box. It's kind of a novel design from that perspective. And it does snapshots and copy services extraordinarily well, which again is an attribute of storage that typically plays in virtual storage environments. So we have a layered architecture that allows you to place function and in particular place management properly deployed. A couple of just sort of quick customer examples. Some mysterious airline manufacturer that evidently sells to American Airlines actually has 14,000 virtual machines running on XIV disk arrays, and they particularly like it because of the evenness of performance. So as these workloads sort of come and go and stand up and stand down, the internal spreading of data across all the arms in an XIV disk array plays very strongly to the requirements of their workload. So does the ability to do quick clones. So as new VM instances are created, you create boot images out of clones, and off you go. And XIV is quite talented in that respect. Another example, some folks doing virtual desktop implementations for 1,200 users. Virtual desktop is sort of a good example of a pedestrian application which doesn't have any enterprise storage requirements at all, which when you cluster it and deliver it as a service now does have enterprise kind of applications. So if I'm doing one desktop, I can do that with a single SATA drive. If I'm doing 1,200 desktops, now I have to be 7 by 24 by 365. And again, XIV is a very good match for this kind of application. Very attractive cost, which is a good big sensitivity in virtual desktop. And then again, a good performance and good copy functions. And then finally, let's see, I guess I have to click through this, don't I? An example of a resiliency facility in VMware language. This is Site Recovery Manager. So what we have is a facility in which replication function performed at the storage layer is used to keep two physically disjoint or remotely separated machine rooms current from a data perspective. The application failover is actually handled by server vMotion on the VMware layer, and those two layers are kept in sync via a set of scripting that say, make sure the data's moved and make sure all the LUN names are correct on the remote location. And in the event of an actual application failover, all the data is waiting on the other side for the new physical servers to take over the in-flight virtual machines and maintain their association to data as they go. Okay, and then there's one last picture. If you don't like SANs, a lot of people don't like SANs or think they're graft and corruption or too expensive or whatever, don't need their performance. There is also a scale-out NAS picture that we've invested in which you create sort of the mother of all NFS or CIFS file servers, and those things can then be mounted either by VMware for things like boot images or LUN images that are managed by VMFS itself, or mounted directly by the application. So bypassing the storage virtualization layer in VMware and going directly, for example, to a data service. So these are the kinds of pictures that people draw in medical archiving applications or large share file server environments for software development, chip design, automotive design, aerospace design, things like that. We have a full portfolio of products, so depending on the size and shape and requirements of your particular application, we probably have something that addresses your needs. And in conclusion, in addressing this question of doing the mapping of storage requirements in the vocabulary of enterprise to virtual server environments, you need kind of a rich tool bag, and we have one. So if you're in the market for such a thing, come see us and we can help you. Okay, that's my story, and I'm sticking to it. Any questions before we're completely out of time for either Bob or I?
Great. Well, thank you very much. Have a great day.